Okay, picture this. You're sitting on a mountain of data, spreadsheets, databases, transaction logs. It's a perfect record of what is what was.
Right, the historical facts.
Exactly. But what if your questions aren't just about historical facts? What if you need to know, like, what could happen?
Hmm.
What if you want to predict future outcomes based on past patterns, spot something truly bizarre that doesn't fit any normal trend? Fill in missing pieces of information, not with simple averages, but, with confident estimates.
Or even generate entirely new realistic scenarios that mirror your real data.
Yeah, that too. And traditional databases, they're great for the what is, but they kind of hit a wall there, don't they?
They really do. As powerful as they are for handling structured queries on static data, they're fundamentally built for that what is world. You ask for records meeting criteria, sum columns, filter rows, standard stuff.
Right.
But when you introduce probability, uncertainty, the need to generate possibilities rather than just retrieve existing facts, well, the standard tools start to struggle.
So you have these probabilistic models which are designed for these kinds of questions.
Exactly. They're great for understanding complexity, generating new data, making inferences.
But getting them to talk to your database is the tricky part.
That's the crux of it. You usually have to pull data out, wrestle it into a different system, write complex custom code, often in these specialized probabilistic programming languages or PPLs, then run your analysis, and maybe try to stitch the results back into your data workflow somehow.
And that stitching together, that hand coding across different systems, that just, well, it sounds complicated.
It is. It screams complexity, potential errors, and frankly, a steep learning curve that puts sophisticated probabilistic analysis out of reach for many who could really benefit from it.
Yeah, it feels like there's this frustrating gap between your data and the powerful probabilistic insights locked away in models.
Precisely.
And that's exactly the gap today's deep dive is designed to explore. We've got a fascinating source here, a technical paper from researchers at MIT and Digital Garage.
Yeah, this looks really interesting. Published in the Proceedings of the ACM on programming languages, no less. So quite formal, quite rigorous.
Definitely signals authority. And it's about a system they've developed called GenSQL.
Right. At its core, the paper describes GenSQL as a probabilistic programming system built specifically for querying. And this is the key phrase: probabilistic generative models of database tables.
Querying generative models of database tables. Okay, that sounds like the heart of it.
Yeah.
So our mission for this deep dive is to unpack this.
Let's do it.
We need to figure out exactly what GenSQL is, understand how it extends the familiar world of SQL to interact with these models, maybe peek under the hood a bit to see how it manages the complexity,
See the mechanics.
learn about the kinds of problems it helps you solve, and most importantly, pull out the key takeaways for you, the listener. How can this give you a shortcut to getting powerful insights from complex data without needing a PhD in probabilistic programming?
Right. Translating the technical details into practical value.
Exactly. We'll navigate the technical stuff together to find those valuable insights.
Sounds like a plan. Let's jump in.
All right, diving right into the core idea. Section 1 of the paper really sets the stage. It defines GenSQL and the problem it's designed to tackle. As you said, it's a probabilistic programming system tailored for querying probabilistic generative models of database tables. Can you break that down a bit more for us? What's the core concept here?
Okay, so the fundamental shift here is thinking of your database table not just as, a static collection of rows and columns.
Like a spreadsheet.
Right. But as a manifestation of some underlying process or distribution. A probabilistic generative model tries to learn and represent that underlying process.
Okay.
So instead of only having the raw data table, which is the historical record of what was, you also have this model. And this model captures the statistical structure, the relationships, the patterns within that data. And because it's generative, it can essentially simulate or produce new data points that are statistically consistent with the data it learned from.
Okay, so it's not just descriptive statistics, averages, counts, summaries. It's building a probabilistic picture of how the data was formed, and it can generate new data points that fit that picture.
Precisely.
Like if your data is customer demographics, the model could learn the typical age, location, purchase patterns, and then generate profiles of hypothetical new customers who fit those patterns.
Exactly right. It captures the joint probability distribution across the columns. It understands, for example, how likely certain combinations of features are, or how a change in one column probabilistically influences another. It gets the relationships.
But the problem, as the paper highlights, is integrating this power with the traditional database operations we all rely on.
That's the challenge.
Why is that integration so difficult? I mean, if you have the data in a database and the model in a probabilistic programming system, why can't they just talk easily?
Well, basically, they speak different languages, and they're built for different purposes. Standard SQL databases are optimized for querying concrete facts. They have sophisticated query planners and engines for filtering, joining, aggregating huge amounts of structured data. Very efficient at that.
Mm-hmm.
Probabilistic programming languages, PPLs on the other hand, they're designed for defining models and running inference algorithms. Things like sampling, calculating probabilities, learning parameters. They don't typically have built-in first-class support for database concepts, like
Mm-hmm.
set-based operations on tables or joins, or even simple projection and selection in the way SQL does. It's just not their focus.
So if I want to, say, find all customers from a specific region, that's a database operation,
Right.
and then ask the model what the probability is that a customer from that filtered group will make a purchase over $100, that's a model operation,
Yep.
and then maybe join that probability back to the original customer records, another database operation. I'd have to write a lot of custom code to move data back and forth and orchestrate all these steps.
Precisely. You'd likely extract the relevant data from the database, load it into your PPL environment, write PPL code to condition the model, and run the inference, collect the results from the PPL, and then potentially load those results back into a temporary database table to combine them with other data. It gets messy fast.
Yeah, that sounds cumbersome.
It is. And that handwritten orchestration is exactly what the paper describes as cumbersome and highly error-prone, especially for complex Bayesian inference workflows that might involve many such steps. Lots of places for bugs to creep in.
And GenSQL's proposed solution is to avoid all that manual labor, to sort of embed the probabilistic reasoning right into the query.
Yes, that's the core idea. They augment standard SQL with a small set of new primitives. These allow you to express operations on the probabilistic model directly within your SQL queries.
Yeah.
This lets you seamlessly mix operations that access raw data records with operations that interact with the model, all in a single declarative query. The aim is to make these complex data analysis and inference tasks concise, readable, and much less likely to contain those subtle bugs that creep into hand-coded workflows.
That sounds incredibly powerful. It's like giving SQL built-in commands for probabilistic reasoning and data generation. What specific kinds of tasks, according to the paper and maybe Figure 1, does this unlock?
Yeah, Figure 1 gives a great visual overview. It shows the kinds of questions you can ask and tasks you can perform directly within GenSQL queries by leveraging the generative model alongside your data. Things like,
Like what?
okay, so predicting values. You can ask the model to predict a value in a column for an existing row, given the other values in that row. Like predicting if a software developer in Seattle is likely to know Rust and getting back probabilities for yes or no.
Okay, prediction. What else?
Detecting anomalies. The model learns the typical patterns, right? So you can query it to identify rows that are statistically very unlikely under its learned distribution. This helps find outliers or potential data errors that stand out not just in one column, but in the context of the entire row.
Context matters. Got it.
Imputing missing data. Instead of just using simple averages, you can use the model to estimate missing values probabilistically. The example shows querying to fill in a missing experience field, and you get back a probability distribution over possible values like 5 years, 3 years, 1 year. You can choose the most likely or even sample from that distribution.
That's much richer than just plugging in the mean.
Definitely.
Mm.
Then there's cleaning noisy entries. Similar to anomaly detection, you can flag entries that have very low probability given the rest of the row's data, suggesting they might be transcription errors or noise.
Finding stuff that just looks wrong.
Right. And finally, generating synthetic data. You can ask the model to generate entirely new synthetic rows that are statistically similar to your original data. This is incredibly useful for testing workflows, generating data for privacy-sensitive scenarios, or even creating hypothetical data sets conditioned on specific criteria.
Like the example in Figure 1, generating plausible age and salary combinations for women in Massachusetts.
Exactly that, generating 1,000 synthetic rows fitting that specific constraint.
These tasks are fundamental to modern data analysis and machine learning. You're moving from just summarizing your data to actively questioning its underlying structure, predicting future points, finding exceptions, and creating realistic simulations. And the big promise here is doing it all with a familiar SQL syntax, or at least SQL-like.
Exactly, SQL-like. And a crucial point the paper emphasizes is the decoupling. GenSQL abstracts away the complexities of the underlying probabilistic programming system and the inference algorithms it uses.
What does that mean? practically?
It means that as a user writing a GenSQL query, you don't necessarily need to know the details of, say, Monte Carlo Markov chains or variational inference or the specific syntax of the PPL used to build the model. You interact with the data and the model using these high-level GenSQL primitives.
So it significantly lowers the barrier to entry for leveraging powerful probabilistic models.
That's the goal. It means data analysts or engineers who are already proficient in SQL can start using these sophisticated techniques without needing to become experts in probabilistic programming first.
That is huge. It creates a clearer separation of concerns. Model developers build and train the best models, and data users query them through a standard interface.
Precisely. It's a core design principle that influences much of the system's architecture, as we'll see.
Okay, so let's get into that. How does this augmented SQL actually look? What are these new primitives they've introduced into the language? Section 3.1 of the paper lays out the syntax extensions.
Right, so they've added a few key clauses and expressions that allow you to interact with a probabilistic model alongside your existing tables.
Okay, first one.
First, for generating new data, you use the generate under model limit end clause. This is conceptually similar to select because it produces rows, but instead of retrieving existing ones, it asks the system to sample n synthetic rows from the specified probabilistic model.
So select gets real rows, generate makes new ones based on the model. Got it.
Then there's the given event clause. This is absolutely fundamental for asking those probabilistic what-if questions.
How does it compare to where?
Well, a standard where clause filters existing data based on conditions. The given clause, on the other hand, conditions the probabilistic model. It tells the model to focus its probability distribution on outcomes that satisfy the given event. This is how you ask what the model predicts or how likely something is given specific circumstances.
Ah, so where filters rows, given influences the model's probabilities. Crucial distinction.
Very crucial. Then they introduce a powerful new join type, table generative join model. This isn't your standard join matching columns between two existing tables.
How does it work then?
It joins each row of an existing data table with a synthetic row generated from the probabilistic model. But here's the really clever part. The generation of the synthetic row from the model can be conditioned independently for each row of the real data table based on the values in that specific row.
Whoa, okay. So for each real row, it generates a custom hypothetical row from the model conditioned on that real row's data.
Exactly. It allows you to explore the model's predictions or implications for each individual data point you have. It enables some very powerful combined queries.
That sounds really unique, combining empirical reality with probabilistic potential, row by row.
It is. And finally, there's a new expression you can use within your select clause or even in where clauses, probability of event under model.
Okay, what does that do?
This lets you compute the probability for discrete events or the probability density for continuous events of a specific event occurring according to the distribution represented by the model. And importantly, this can be done after the model has been conditioned using given. This allows you to quantify likelihoods directly within your queries.
So you can actually get numbers back, like the probability of X is 0.7 given Y.
Precisely. Probabilities or densities right in your results.
That generative join still sounds like the most complex, but also maybe the most powerful addition.
It enables some very advanced analyses, like the example we'll look at. But before that, it's worth clarifying what they mean by the model in these queries.
Right, the model part.
It's a probabilistic generative model that has learned the statistical structure of your database table. The paper notes these models can be automatically learned from data using techniques like probabilistic program synthesis they mentioned using a system called Crosscat in their evaluation.
Okay, so it can build the model for you sometime.
Or they could be hand-designed statistical models, or a hybrid. The crucial part, technically, is that for a model to work with GenSQL, it must adhere to a specific formal contract or interface. They call this the Abstract Model Interface, or AMI. We'll definitely come back to that.
Okay, so any model that speaks the AMI language can be queried by GenSQL. Makes sense. And you mentioned something about events and event zero. This shows up in section 3.1 and figure 4. What's that about?
Right. So an event in GenSQL, using given or probability of, is basically just a Boolean expression about the potential state of a row. Think age 65 and D city equals Boston, or sales 1,000. It's how you specify conditions for conditioning the model or ask about the probability of certain outcomes.
Pretty much like a condition and aware clause, but aimed at the model's potential outputs, not the existing data.
Exactly. Now, the distinction they make with events here is a bit technical, but it's important for correctness, especially with continuous variables. In probability theory, the chance of a continuous variable like, say, weight or height taking on an exact specific value, like exactly 175.345 pounds, is technically zero. The probability density is zero at that single point.
Right. You usually talk about ranges for continuous variables.
Exactly. Trying to condition a probabilistic model on an event that has zero probability density in this way is mathematically tricky. It requires careful handling in probabilistic programming systems. GenSQL introduces event zero expressions and a type system that correctly deals with conditioning on these zero probability density events.
So it's handling a known, tricky edge case and probability to make sure the math works out correctly, even when you ask about exact continuous values.
Precisely. It shows the formal rigor they've built into the system to ensure the probabilistic calculations are sound.
And speaking of formal structure, Figure 4 also shows a type system, and these symbols, I and no, what are those about?
Yeah, Figure 4 shows the type system, which extends standard SQL types to include concepts needed for probability, like row model and event. The symbols, gamma and delta, are standard notation from formal language theory, basically representing the context or environment.
Context.
Typically holds the global schema information, what tables and models are available overall. Table holds information about identifiers that are currently in scope within a particular part of the query, like the columns available from the table being processed in a select statement. It's part of the formal machinery they use to precisely define the meaning, the semantics of GenSQL queries.
Got it. So the formal foundations are there to guarantee correctness. But the real power for the user comes from combining these new primitives. Let's look at that complex health data example in Figure 2. Estimating conditional mutual information between age and BMI given patient weights. That sounds advanced.
It really is. Conditional mutual information, it's a measure of how much knowing the value of one variable, say BMI, tells you about another, say age, given that you already know the value of a third variable, like weight.
Okay, so how related are age and BMI specifically for people of a certain weight?
Exactly. It's used to understand dependencies that might only exist or be stronger within specific subgroups of your data. Calculating usually involves integrating over probability distributions, which is computationally pretty challenging.
And the GenSQL query in Figure 2 accomplishes this complex statistical calculation. Let's walk through it slowly. It starts like a standard SQL query, calculating an average, grouping by weight, but the from clause looks nested and complicated.
Right. Look at the inner query on lines 15, 17. It starts with health data duplicate 1,000 times. That's not standard SQL.
Definitely not. What's duplicate doing?
It's a GenSQL extension. It tells the system to replicate each row of the health data table 1,000 times.
Why would you want to duplicate your data like that?
This is setting up for a Monte Carlo estimation. Mutual information is related to probabilities and densities. In the context of a probabilistic model, you can estimate these by sampling. By duplicating the original data rows, they create a structure where, for each original patient, they'll have 1,000 identical data rows ready to drive samples from the model.
Okay, so 1,000 copies of each patient's record. Then what happens on line 16? That's the generative join.
That's the crucial step. Health data duplicate 1,000 times generative join H model given hmodel.weight equals health data.weight. This joins those duplicated real data rows with synthetic rows sampled from the model.
And the given clause is key here.
Absolutely. Given hmodel.weight, health data.weight, this is the Perot condition we talked about. For each of the 1,000 copies of a specific patient's data row, say, a patient weighing 150 pounds, this clause tells the model. Generate a synthetic row, but only consider outcomes where the generated weight from the model is equal to that specific patient's weight, 150 pounds.
Wow. Okay, so for a patient who weighs 150 pounds, it generates 1,000 synthetic rows from the model, and each of those generated rows will represent a plausible combination of other features like age and BMI, given that the weight is fixed at 150 pounds. It's like sampling from a very specific slice of the model's probability distribution defined by the real patient's weight.
You nailed it. It's sampling from the conditional distribution of the model, given the observed weight from the real data row. The generative join then combines the real data row, or its copy, with this conditioned synthetic sample from the model.
So the result is a big intermediate table.
A very large intermediate table, yeah, where each original patient row is represented 1,000 times, and each copy is paired with a different model sample conditioned on that patient's weight.
That is a really elegant way to combine real data points with model-based simulations of what's probable given those specific data points.
It is. And then, from this intermediate table, which they aliased as table on line 17, that contains pairs of real weight and model-generated age BMI values, conditioned on weight, the rest of the query calculates the terms needed for the mutual information formula. Look at line 611. They use probability of expressions within the select clause.
Right, like probability of hmodel.age equals table.age and ehmodel.bmi under hmodel given hmodel.weight hme on hpna. Okay, that's a mouthful. What is it asking?
It's asking the model, conditioned on the real patient's weight via given hmodel.weight equals table.weight, for the probability density of observing the generated age and BMI values, table.a, table.bmi, from that specific row in the intermediate table.
Okay, so it gets the joint probability density, PSI, of the generated age and BMI, given the weight.
Yes. And lines 811 calculate the marginal densities, px for age, pi for BMI. Similarly, GenSQL translates these probability of calls into calls to the underlying model's function for calculating log probability density, often called log PDF. Then lines 3 to 4 calculate the logarithm of the ratio of these densities, all px pi plus log pi. That specific calculation is the core term in the mutual information formula.
And because each original patient weight now has 1,000 associated rows in the intermediate table, the final select AVG group by weight calculates the average of this term for each original weight.
Which gives the Monte Carlo approximation of the conditional mutual information for that specific weight.
Wow. Okay. So this single query orchestrates duplicating data for sampling, performing a generative join with Perot conditioning, querying probability densities from the model for the generated samples, and finally using standard SQL aggregation to get the desired statistical measure.
Exactly. Doing this manually would involve significant data handling code intertwined with PPL inference code. Lots of potential for errors. The paper uses this example really effectively to demonstrate the expressivity and conciseness that GenSQL provides for these complex workflows.
It really does. It makes a very complex statistical analysis feel almost like a standard data query, albeit with some new keywords. But how does GenSQL achieve this under the hood? How does it translate this SQL-like syntax into actions that interact with a probabilistic model, especially if that model was built using a different language or system?
That brings us nicely to section 3 and 4, where they discuss the formal semantics and, crucially, the abstract model interface, the AMI.
Okay, formal semantics, we touch on this. In plain English, what is that again, and why is it important for GenSQL?
Right. Formal semantics is essentially providing a precise mathematical definition of what every valid query in GenSQL means. For a system dealing with probability and generation, this is critical. You can't have ambiguity.
It needs to be exact.
It ensures that a query isn't open to interpretation. There's a clear, unambiguous mathematical definition of the probability distribution or set of values the query should produce. The paper provides a measure-theoretic denotational semantics, which is a very rigorous way of doing this. Think of it as the ultimate rulebook that defines the expected probabilistic outcome of any query, regardless of how it's actually implemented or computed.
So it's the foundational math that guarantees the query results are correct according to probabilistic principles. It defines the truth the system aims for.
Exactly. It's the theoretical grounding that ensures correctness, particularly when you're combining data operations and probabilistic operations. They described interpreting data as sets or bags of tuples, table mode, and probabilistic outputs as probability measures, row models. This formal framework is what allows them to reason about improved properties of the system later on.
All right, so the semantics tell us what the query means, but the system still needs to do something to get that result, and it needs to interact with potentially different probabilistic model backends. That's where the AMI comes in, right?
Yes, the abstract model interface, AMI, introduced in section 4, is really the key to GenSQL's flexibility and its ability to work with various probabilistic models.
How so?
The AMI defines a standard set of capabilities, essentially, a contract that any probabilistic generative model of tabular data must expose or implement to be compatible with the GenSQL system. It's the bridge between the high-level GenSQL query language and the low-level implementation details of the specific probabilistic model being used.
Ah, okay, so it's like a universal adapter or a standard API for probabilistic models, like USB for models.
That's a great analogy, actually. Precisely.
Right.
Regardless of whether your model was built using Python, a specific PPL like Gen or SPPL or some other system, as long as it can satisfy the requirements of the AMI, GenSQL can query it.
So what does the AMI actually require a model to do? What are the standard capabilities?
It requires any compliant model to implement three core methods. First, simulate. This method must be able to generate samples from the model's distribution. Crucially, it must also support generating samples from the model conditioned on specified events, like in our generative join example.
Okay, sampling.
Second, log PDF. This method computes the logarithm of the probability density for continuous data or probability mass for discrete data of a given data point under the model. It also needs to support computing this density or mass under conditioning.
Density or probability mass, got it.
And third, prob. This method computes the probability of a specific event occurring under the model, again, potentially conditioned. This is used for discrete events where the probability isn't necessarily zero, unlike a single point in a continuous distribution.
Okay, sample, density mass, or probability of an event. Those seem like the fundamental operations you'd need from pretty much any probabilistic model, right?
They really are the core building blocks for probabilistic inference. By standardizing these three operations, GenSQL can interact with anything that provides them.
And the benefit is interoperability.
Exactly, and the benefit is significant.
Yeah.
As the paper mentions, section 4.1, they've actually implemented the AMI for models built with different backends, including crosscat models implemented in ClojureCat and models in the SPPL probabilistic programming language. This capability is a major contribution because it enables true multilanguage workflows.
Meaning?
It separates the concerns of model development and model usage. You can pick the best PPL or modeling technique for your specific data problem, train your model. As long as you wrap it so it presents itself via the AMI, GenSQL users can query it using the standard GenSQL language without needing to know the internals of that specific PPL.
That's powerful. It opens up a whole ecosystem of different models to be queried through a single consistent interface. So, okay, I write my GenSQL query, which expresses what I want to know. How does the system figure out which AMI methods to call on the specific backend model and in what sequence to actually compute the answer?
That's the job of the GenSQL query planner and the lowering process. This is described in section 4.2 and illustrated nicely in figure 7. The query planner acts much like a compiler for your GenSQL query.
Like a SQL query planner, but for this extended language.
Exactly. It analyzes the query and translates it into a series of calls to the methods defined in the AMI. Simulate, log PDF, prob.
How does that translation work?
It involves two main steps. First, normalization, which simplifies the complex GenSQL query structure into a more basic canonical form. And second, a program transform that translates this normalized query into a simpler, lowered language. This lowered language operates on concepts like bags of tuples and consists of basic functional operations, think map, filter, join, combined with explicit calls to the AMI primitives. Figure 6 shows what this lowered language looks like. It uses identifiers like simulate, logpdefeed, probid, which correspond directly to the AMI methods.
So I write something relatively high level like generative join, and the query planner automatically translates that into the necessary sequence of joins and row-wise calls to the simulate method of the underlying model's AMI implementation, handling the conditioning specified by given.
Precisely. You express your intent declaratively in GenOL, and the system automatically generates the execution plan involving calls to the model's capabilities via the AMI. Figure 7 shows how different GenSQL clauses are transformed. Generate under translates to replicating data and calling simulate. Probability of translates to calls to log, PDF, or prob, and then maybe exponentiating. Generative join translates to that combination of joining and row-wise calls to simulate. This automated translation is absolutely key to simplifying the user's experience and preventing those hand coding errors.
This level of formal definition, the semantics, the clear interface like the AMI, suggests that the system might also provide some guarantees about the results you get. Does the paper discuss this? Can I trust the numbers?
Absolutely. They highlight this as a major contribution in sections 4.3 and 4.4. GenSQL provides formal soundness guarantees about the correctness of the query results. But the nature of the guarantee depends on how the underlying probabilistic model backend implements the AMI.
Okay, different guarantees depending on the backend model. Tell me more.
They offer two main types. First, the exact AMI guarantee. This is covered in section 4.3 and theorem 4.2. This applies if the underlying probabilistic model backend provides an exact implementation of the AMI methods.
Meaning the samples are drawn from the truly exact distribution, and the densities or probabilities are computed exactly with no approximation.
Right. This is possible for certain specific classes of probabilistic models, often ones that can be represented in languages designed for exact inference, like SPPL, which they mentioned. If the model backend provides these exact simulate log PDF and prob functions, then GenSQL queries that are translated via this formal semantics are guaranteed to produce results that are also semantically exact.
So if I query for a probability using an exact backend, I get the mathematically precise probability.
Yes. Or, if you ask it to generate data conditioned on an event, it samples from the exact conditional distribution. No approximation involved in the result, assuming the backend is truly exact.
That's a very strong guarantee. It means for certain types of models, the results from GenSQL are as precise as the underlying mathematics allows. But what about the more general, complex models where exact inference is computationally intractable? Most real-world probabilistic modeling relies on approximation techniques like Monte Carlo sampling or MCMC, right?
Yes, exactly. And GenSQL explicitly addresses this very common scenario with the approximate AMI guarantee. This is laid out in Section 4.4 and Theorem 4.3. This guarantee applies when the underlying AMI implementation of the backend relies on approximate inference methods.
Okay, so even if the model itself is approximate, I can still get some kind of guarantee. How does that work?
Yes. The guarantee is based on the concept of asymptotically sound estimators. This is a statistical idea. It means that the results provided by the AMI methods, simulate log PDF, prob, don't have to be exact for any single run, but they must statistically converge to the true, exact semantic value as you provide more computational budget.
Like letting a sampler run longer or using more particles in a Monte Carlo method.
Exactly. If your AMI implementation uses estimators that are asymptotically sound in this way, and your GenSQL query is what they call safe, meaning it avoids certain constructions that become problematic with approximation, like trying to make exact comparisons against values that are only known approximately.
Okay, so some reasonable constraints on the query.
Right. If those conditions hold, then the result of your GenSQL query are also guaranteed to be asymptotically sound or consistent.
What does asymptotically sound mean for the query result itself? What do I actually get?
It means that if you run the query multiple times, or with increasing computational resources dedicated to the underlying model backend, the sequence of results you get will converge in probability towards the true, exact semantic value the query represents, according to the formal definition.
Okay, let me see if I get this. It's like taking a picture with a lens that needs focusing. Each shot might be slightly blurry, that's the approximation, but as you turn the focus ring, increase the computation budget, the picture gets clearer and clearer, converging on the true image.
That's an excellent analogy. That's exactly the idea. You get meaningful statistical approximations that improve predictably with more computation. It formalizes the practical trade-off you often make in probabilistic modeling. You could use expressive, general models that require approximation, but you still have formal confidence in the quality and convergence of your results.
Okay, so you have formal confidence whether you're using an exact or an approximate backend. You just need to understand the nature of the guarantee in each case. That makes GenSQL seem like a robust system for both theoretical exploration and practical applications.
That's the argument they make, yes.
Formal guarantees and clear semantics are impressive, definitely. But in the real world, people care about whether it's actually fast enough and easy enough to use, the practical side. How did GenSQL perform in their evaluation? Section 5 talks about this.
Right, Section 5 details their performance benchmarks and usability comparisons. They evaluated their implementation, which, by the way, is open source and written in Clojure against other systems. Primarily, they compared it to BaseDB, which they identify as a related system for querying probabilistic models of data.
Okay, so how did GenSQL stack up on speed? Table 1 and Figure 8 have the performance data.
On a set of benchmark queries focused on computing probability densities, GenSQL using different probabilistic model backends via the AMI consistently showed significant speedups compared to BaseDB. Table 1 reports speedups ranging from 1.7x all the way up to 6.8x, with an average speedup of about 4.3x.
That's quite substantial.
It is, and Figure 8 is particularly illustrative for these probability calculations. It shows that GenSQL, specifically when using an exact SPPL backend via the AMI, produces exact results for probability queries with very low variance. In contrast, BaseDB using rejection sampling produces approximate results that have higher variance. The answers jump around more regardless of whether they fix the number of samples or aimed for a fixed acceptance rate.
So GenSQL was not only faster on average for these tasks, but also capable of being more precise, even exact, when using the right backend.
That's what the results suggest, yes. better for speed and potentially better for exactness.
What contributed to these performance gains? Was it just the backends they used?
The paper attributes it to several factors. Yes, the specific probabilistic programming backends they integrated via the AMI, like ClojureCAD and SPPL, were often faster than BaseDB's default backend for these tasks. But also, GenSQL applies reusable database-style optimizations at the query planning level, which helps. And they suggest the implementation language itself, Clojure, is quite performant.
You mentioned reusable optimizations. What kind of optimizations can GenSQL apply automatically? Figure 9 gives some clues, maybe.
Yeah, similar to how a traditional database query optimizer works, GenSQL's planner can apply optimizations that improve efficiency regardless of the specific probabilistic model being used underneath. These include things like caching results of frequently needed computations like condition models or likelihoods, so they don't need to be recomputed repeatedly within the same query or across queries.
Smart. Don't compute the same hard thing twice.
Exactly. They also exploit learned independence relations between columns, which is detailed in Appendix B. If the model understands that, say, column A and column B are independent given some other column C, the query planner can use that knowledge to simplify calculations involving A and B in the context of C.
That makes sense. If predicting one column doesn't depend on another column given everything else I know, the system shouldn't waste computation modeling the second column's influence in that specific context.
Precisely. And Figure 9 shows the impact of these optimizations. Figure 9a compares optimized GenSQL to unoptimized GenSQL and also to handwritten ClojureCAD code for the same task. The optimized GenSQL version is significantly faster than the unoptimized one and gets pretty close to the performance of the raw hand-tuned code.
So the optimizations really work.
They seem to. Figure 9b shows that optimizations not only speed up generation queries, generate under, but also reduce the variance, the unpredictability of the execution time. And Figure 9c demonstrates that the system scales reasonably well, the time increases, but not explosively with increasing numbers of rows in the data table when performing queries that involve interaction with the model.
Okay, so the system doesn't just provide a high-level language, it translates that language efficiently by applying smart optimizations. That covers performance. But beyond speed, the other half of practicality is usability. How much easier is it really to write these complex queries in GenSQL compared to just using the PPLs directly?
This is arguably one of GenSQL's biggest selling points, and they put a major focus on it in Section 5.1 and Figures 10 and 11. Just look at Figure 10. It compares the GenSQL code for a conditional probability query to the equivalent code you'd have to write in pure ClojureCAD or in SPPL accessed via Python.
Wow. Okay, yeah. The GenSQL query, Figure 10a, is what, 6 lines maybe? And it looks quite readable if you know SQL. Select this probability under this model, given these conditions from this data. It really feels like you're just stating the question you want to answer.
Exactly. It's declarative. Now compare that to Figure 10b, the ClojureCAD version, or 10c, the STPL Python version. In ClojureCAD, you need to manually iterate through the data rows, extract the relevant parts for conditioning, call the model-specific log PDF function with the correct arguments for each row, handle the results, collect them.
It's a lot more imperative, step-by-step instructions.
Yes. And the SPPL Python code requires similar manual iteration using something like iteros on a data frame, accessing specific columns, calling the models method inside the loop. It's significantly more code, and it's operating at a much lower level of abstraction. You're managing loops, data structures, and explicit function calls for each step of the inference process.
And the paper says this manual approach is error-prone.
Right. They explicitly call this hand-coding approach error-prone and provide concrete examples. The SPPL code in Figure 10c, for instance, would apparently crash if there were missing values, like nan, in the data, which is a common issue. GenSQL's system is designed to handle missing values more gracefully during inference.
Okay, that's a practical benefit.
And the ClojureCAD example in Figure 10b they mentioned had a subtle bug related to type mismatches in the dictionary keys used for conditioning. This caused the conditioning to silently fail and produce incorrect results. These are exactly the kinds of implementation details and potential pitfalls that writing raw PPL code exposes you to.
Whereas GenSQL seems to hide all that complexity. You express the high-level query, and it takes care of the low-level details of interacting with the model via the AMI, including things like handling missing values correctly.
That's precisely the gain they're aiming for. It elevates the user's interaction from implementing how to compute the probabilistic result to simply stating what result they want. Figure 11 provides another great comparison, looking at GenSQL's generative join, Figure 11c, versus the workflow needed to achieve a similar result in BaseDB, figure 11t.
How does BaseDB handle it?
In BaseDB, based on their figure, achieving a similar outcome requires dropping out of the probabilistic inference environment into a standard SQL environment. They show escape into SQLite, then manually altering tables, inserting special placeholder rows to represent the generation task, and then using a separate NFR command later. It's a multi-step, less integrated process.
Yeah, that sounds much clunkier than GenSQL's single generative join clause, integrating the operation into one cohesive query structure.
Exactly. And just to put a finer point on the code savings, the paper mentions in Appendix A, Tot 1, that a simple query on a conditioned model that takes a single line in GenSQL requires over 50 lines of code when using a standard machine learning library like scikit-learn to achieve the same thing.
50 lines versus 1.
For that specific example, yes. It really underscores the magnitude of the usability advantage GenSQL aims to provide for querying probabilistic models.
Okay, so the takeaway here is, not only is it potentially faster and backed by formal guarantees, but it also seems to make expressing complex probabilistic data tasks vastly simpler and less error-prone for the user. The practical benefits seem pretty clear.
That's the case they make, quite convincingly, I think.
So let's look at the real-world case studies they include in Section 5.2. Where have they actually applied GenSQL to solve concrete problems? Show us the impact.
Okay, the first case study involves anomaly detection in clinical trial data. They used data from the BEAT-19 clinical trial, which focused on COVID-19. The challenge in clinical trials, as you can imagine, is understanding complex patient data and identifying unusual cases. These might signal anything from simple data entry errors to potentially interesting or unexpected medical findings that warrant further investigation by the researchers.
Makes sense. Lots of data, need to find the weird stuff. How did GenSQL help them find those anomalies? Figure 12 shows the query they used.
Right, Figure 12a shows the GenSQL query. They selected relevant patient features, things like BMI, exercise habits, self-reported health status, age, sex, etc., from the clinical trial records table. They did apply an initial standard where clause first, just to filter out rows with values that were simply extreme outliers on a single dimension, like a BMI that's physiologically impossible regardless of context.
Okay, basic sanity check first.
Right. Then the core of the anomaly detection is the main where clause. Probability of BMI under clinical trial model given, 0.01.
Given, what does the asterisk mean there?
The given is a convenient shorthand, mentioned back in Section 3.1. It means conditioned on all the other values in this row.
Ah, okay.
So for each patient record, the query asks the clinical two-file model, which has learned the statistical structure of this data. What is the probability density of observing this patient's specific BMI value, given the values of all the other columns for this patient, their age, sex, health status, exercise levels, and so on? If that calculated probability density is extremely low, less than 0.01 in this query, it means this BMI value is very unlikely given the specific context provided by the rest of the patient's data. That row is then flagged as an anomaly.
That's a really powerful way to find context-specific outliers. It's not just finding people with high BMIs or low BMIs, but finding people whose BMI is unusual given their specific overall health profile and habits. Much smarter than simple thresholding.
Exactly. It leverages the model's understanding of the joint distribution.
So what kind of anomalies did they actually find using this query?
Figure 12b shows the results. Figure 12b shows that the query flagged 8 participants as anomalous. And when they investigated these specific records, they found something quite interesting. All 8 individuals were clinically obese, with a BMI over 30. Now, that itself wasn't necessarily rare in the data set, but the key was that these specific participants also reported above average, or even well above average, health status and exercise levels compared to others in the trial.
Ah, I see. So the model had learned that within the typical distribution of people reporting high health status and high exercise levels, a clinically obese BMI is statistically quite unlikely. It wasn't just flagging high BMIs, it was flagging BMIs that were anomalous in that specific context of otherwise healthy reported indicators.
Exactly right. Figure 12 helps visualize this. The black points show the distribution of BMI for individuals who were similar to the anomalies, high health exercise reported, while the red points are the anomalies themselves. You can clearly see the red points are outliers within that specific group.
Yeah, they stick out from the black cloud.
And Figure 12e shows how the conditional probability, p-BMI, the probability given the context, is much lower than the marginal probability, p-BMI, for these anomalous points. They fall below the diagonal line, confirming they are indeed unusual given their context. Figure 12C just shows the overall learned relationship between BMI and health status exercise in the model.
This really demonstrates the real-world value. Researchers could use GenSQL to automatically sift through complex trial data and find patients who might have data errors, like a typo in BMI or exercise reported, or, perhaps more interestingly, represent genuinely unusual clinical cases that deserve deeper manual review.
It turns the probabilistic model into a sophisticated tool for data auditing and exploration, made accessible via a relatively simple query.
Okay, really cool application. The second case study is in synthetic biology, creating a virtual wet lab for engineering bacteria. That sounds very futuristic.
It is pretty cutting-edge stuff. The problem they're tackling is that experiments in synthetic biology, like designing genetic circuits to make bacteria produce useful molecules, or understanding how existing circuits work, are notoriously expensive and time-consuming. Running just one experiment in a physical lab, a wet lab, can take days or weeks and require costly reagents and equipment.
Right, biology takes time.
It does. So researchers desperately need ways to predict the outcomes of potential genetic designs or experimental conditions before they commit to the physical wet lab. They want to simulate the experiment virtually first.
Makes perfect sense. Reduce the trial and error. What kind of data are they working with for this?
They're using gene expression data from E. coli bacteria. This data records how active thousands of different genes are under various different experimental conditions, like when you add specific chemicals, inducers, that are known to turn certain genes on or off. Learning the complex, often nonlinear interactions between these genes and the experimental conditions from this data is key to predicting how this system will behave.
Okay, complex gene interactions. And how does GenSQL help build this virtual lab?
They use GenSQL primarily for its conditional generation capability. They generate synthetic gene expression data that is conditioned on specific experimental conditions they want to simulate. Figure 13 illustrates this really well.
How so?
Figures 13a and 13b first show scatter plots of expression levels for a few key genes. 13a is from the real experimental data. 13b is from synthetic data generated by GenSQL without any specific conditioning, just using generate under gen expression model limit 1000. You can see the synthetic data, 13b, accurately captures the overall patterns, the shapes, and distributions seen in the real data, 13a.
Okay, so the model learned the general structure of gene expression pretty well.
Right. But the really powerful application here is the conditional generation. Figures 13c and 13e show GenSQL queries using generate under gene, given conditions of 1000. They condition the gen expression model on specific input conditions. For example, adding chemicals like IPTG or arabinose, which are commonly used to induce or trigger gene expression in E. coli experiments.
So figure 13c simulates the scenario where you add IPTG but not arabinose, and figure 13e simulates adding both.
Precisely. And figures 13 and 13 show the synthetic data generated by GenSQL under those exact conditions. What's remarkable, and the key result here, is that the synthetic data distributions generated under these specific conditions, 13 and 13, accurately reflect the outcomes observed in real-world experiments performed under those same conditions. The model correctly captures how the complex network of gene interactions responds to these external inputs, even showing the nonlinear effects.
That's incredibly useful. It means a researcher can use GenSQL to pose a hypothetical experiment. What happens if I add IPTG and arabinose, run a query, and get back a simulated data set that looks statistically like the real experimental outcome would before they ever step into the physical lab?
Exactly. It effectively creates a virtual wet lab where they can test hypotheses, predict likely outcomes, and perhaps optimize experimental designs just by querying the model. This can save vast amounts of time and resources compared to doing all the trial and error in the physical lab.
That's a game changer for that field, potentially. And they showed that simpler models or other general purpose techniques couldn't do this as well, right? I think figure 14 shows some comparisons.
Yes, exactly. Figure 14 shows how simpler models like linear regression, figure 14a, completely fail to capture the complex, nonlinear relationships in the gene expression data. The patterns are all wrong. They also compared against a more advanced generative model technique, a conditional GAN called CT-GAN, shown in figure 14b.
How did the GAN do?
While GANs can be very powerful, the paper notes that for this specific dataset, which is relatively small by deep learning standards, around 943 rows, but contains these complex nonlinear dependencies, the CT-GAN also struggled to accurately reproduce the data characteristics and the conditional distributions compared to the generative model used by GenSQL, comparing 14b back to 13b.
So the underlying probabilistic model they used with GenSQL was just better suited for this particular problem.
It seems so. This highlights that GenSQL's strength isn't necessarily in providing the model itself, but in providing a powerful interface to query high-quality, potentially complex generative models, like the Crosscat model they likely used here, that are well-suited to the data structure. GenSQL lets you leverage the power of the right model.
These case studies vividly demonstrate how GenSQL translates sophisticated probabilistic modeling into practical tools for real-world problems, from ensuring data quality in medicine to enabling predictive simulation in biology, all made accessible through a query interface. It makes the abstract ideas very concrete.
They really do. They show that GenSQL is not just a theoretical concept or language design exercise, but a system with tangible benefits for applying probabilistic inference to real tabular data problems.
Okay, so bringing it all together then. Section 7 of the paper summarizes GenSQL's key contributions and its potential broader impact. From their perspective, what are the main takeaways? What makes GenSQL unique or important?
The paper highlights three primary contributions that they believe differentiate GenSQL and pave the way for its future impact.
Okay, number 1.
First, the multi-language workflows via AMI. This is really crucial. By standardizing the interface through the abstract model interface, GenSQL allows users to leverage models built in various probabilistic programming languages or systems without needing to become an expert in each one.
We talked about this at the interoperability.
Exactly. It establishes a vital separation of concerns. It allows model developers to use the best tools for building and training their models, while data users can query these models using a single consistent language, N equal. Before GenSQL, this kind of multi-language integration wasn't really standardized for querying generative models of tabular data.
Okay, contribution 1, bridging PPLs with the AMI. What's 2?
Second, the declarative querying. They argue that no other system provides such a concise, high-level, SQL-like language specifically designed for expressing these complex probabilistic inference tasks that seamlessly interleave operations on both observed data tables and learned probabilistic models. As we saw, writing these workflows manually in raw PPL code is cumbersome, complex, and error-prone. GenSQL aims to drastically simplify this.
Makes sense. Contribution 2, simplifying complex inference queries. And the third.
Third, reusable performance optimizations. Because GenSQL operates at the query language level, its query planner can apply general database-style optimizations like caching results and exploiting learned independence between variables. These optimizations benefit performance regardless of the specific data or the particular probabilistic model being queried underneath, as long as the underlying AMI implementation can provide the necessary information, like independence.
So you get efficiency gains automatically without needing to manually tune the underlying PPL code for every query.
That's the idea, providing automatic reusable optimizations.
So it's about breaking down silos between modeling languages, making complex tasks easy to express, and providing built-in performance benefits. That sounds like a solid set of contributions. What do they see as the exciting potential paths forward or the broader impact of a system like this? Where could it go?
They suggest several pretty promising directions in Section 7. One is integration with DBMS. Imagine GenSQL becoming a first-class query language extension within standard database management systems, like PostgreSQL or others. You could query your probabilistic models using essentially the same interface and tools you use for your raw data. That would make these capabilities much more widely accessible within the existing data infrastructure.
Yeah, that would be huge, running these queries right inside the database.
Another is querying synthetic data. With growing concerns about data privacy and also the need for large data sets for testing and development, the ability to generate and query high-fidelity synthetic data is becoming increasingly important. GenSQL can make it easy to generate synthetic data sets on demand, maybe conditioned on specific properties you need, and then analyze them using the same query language, potentially without ever needing to access or expose the sensitive real data directly for many downstream tasks.
Interesting. Using the model as a privacy-preserving data source.
Potentially, yes. And finally, they point to the potential for modular development. By creating this clear abstraction layer, the AMI, between the user, writing queries, the model developer, building models using various PPLs, and the PPL backend developer, implementing the AMI for their language, GenSQL promotes a more modular ecosystem.
How is that different?
Well, this separation of concerns is analogous to the physical data independence that relational databases brought us decades ago. Users didn't need to know how data was stored on disk to query it. Similarly, GenSQL users don't need to know the deep internals of the generative model or the PPL it was built with to ask useful questions. This modularity could make deploying and using complex generative models for tabular data safer, more robust, and ultimately more widespread, fostering trust and collaboration.
That modularity angle is really insightful. It suggests that using powerful AI and probabilistic models for data analysis could evolve to be as structured and reliable as using relational databases became, with clearer roles and responsibilities for different parts of the system. Less like fragile custom code, more like dependable infrastructure.
It's a compelling vision for democratizing access to sophisticated probabilistic modeling, making it feel as queryable and integrated as standard data analysis while maintaining the necessary rigor and performance.
So summing up this deep dive then, GenSQL emerges as a system that equips you with a SQL-like language specifically designed to query complex probabilistic models built from your tabular data. This allows you to go way beyond just retrieving historical facts,
Right.
to asking questions about potential outcomes, probabilities, anomalies, and even generating realistic simulations, all within a pretty familiar query framework.
It really provides a powerful shortcut, doesn't it, to understanding not just what has happened in your data, but what could happen, how likely different scenarios are, and maybe even getting a glimpse of the underlying generative structure driving your observations.
Yeah, and it enables you to ask these sophisticated probabilistic questions concisely, backed by formal guarantees about correctness, whether exact or approximate, without demanding you become a probabilistic programming expert overnight.
It truly transforms your data and its learned probabilistic structure into a dynamic, queryable entity, more than just a static table.
That capability feels like a missing piece in the standard data analysis toolkit, honestly. It makes me think about countless data problems where standard SQL queries felt limiting, where I really wished I could ask the data, what if, or how likely is this, given that, but was held back by the sheer complexity of setting up and working with separate probabilistic models.
I know exactly what you mean.
And perhaps that's the provocative thought to leave with you, the listener. Just as relational databases fundamentally changed how we manage and interact with static, factual data decades ago, could systems like GenSQL represent a similar fundamental shift in how we manage and interact with data that is inherently dynamic, uncertain, and maybe best understood through a probabilistic lens?
It's a big question. What new types of insights, discoveries, or applications might be unlocked if querying the probabilistic nature of data becomes as integrated and straightforward as querying a static table is today?
It definitely opens up some fascinating avenues to ponder. Makes you think, what kind of data problems are you facing right now that might be unlocked by asking not just what is true in this table, but what could be true according to this model? Something to think about until the next deep dive.
Indeed, lots to chew on there.
Well, thanks for joining us for this deep dive into GenSQL. We really hope this gave you a valuable shortcut to understanding this exciting development happening at the intersection of data systems and probabilistic programming.
Hope it was useful.